Namaste. Welcome to the next video of Machine Learning Techniques course. In this video, we'll use the logistic regression implementation to fit a circular decision boundary between two classes. In the last video, we used the logistic regression implementation to fit a linear decision boundary between two classes. So here is a different setup where two classes are not linearly separable, but instead there is a circular decision boundary separating two classes. So for this demonstration, we will generate samples from two classes such that they are separated by a circular decision boundary. So we have make_circles utility in sklearn.datasets that we will use to generate such samples. So we get a feature matrix and label vectors, feature matrix and label vector from make_circles. So here we are using two features for every example and we are generating 50 examples each. And label vector, you can see that it's a vector with 50 samples, and feature matrix has again 50 samples each with two features. Now we perform a sanity check where we compare the first element or the first element of shape of feature matrix along with the first element of shape from label vector. It helps us to make sure that the number of rows in feature matrix and label vector are the same. So this assertion succeeds, which means that both feature matrix and label list or label vector have the same number of rows. As the next step, we will make use of polynomial feature transform to transform the features to polynomials of desired degree. Here we know, because we ourselves had generated the data, we know that our data is our classes are separated by circular decision boundary, and in order to learn the circular decision boundary, we have to use polynomial of degree 2 in the features. So note that we would not have such an idea in real world problem settings. So there we perform hyperparameter search to determine the right degree for polynomial transformation. We'll learn more about it in machine learning practice course. Another option is to use model diagnostic tools. We have discussed about it in the initial part of machine learning techniques course. In this case, if the model is underfitting, then we need to increase the degree of polynomial. On the other hand, if the model is overfitting, we can reduce the degree of polynomial or increase regularization penalty. Here we use polynomial transformation with degree 2. So we call polynomial_transform function by passing the feature matrix and degree equal to 2 as arguments. So we get polynomial feature transformation, we get a feature matrix in the polynomial space with the second degree polynomial. Now here we have printed the shape of feature matrix or the number of features in feature matrix before and after transformation. So before transformation we had 2 features, and after transformation we have 6 features. So there are 4 additional features that we got from transformation. These 4 features include a dummy feature corresponding to bias that is set to 1, then square of original features that adds 2 features, x1 squared and x2 squared, and then one more feature corresponding to interaction between 2 features, which is x1, x2. Let's look at first 5 samples from original and transform feature matrix to verify this phenomenon. So you can see that in the transform feature matrix, these 2 features, right? So the first feature and the second feature is copied over here. This is the first feature of the first sample, which is 0.8, and the second feature of the first sample, they are identical, and you can see that the same trend applies here, right? So this is the first feature of the second sample, second feature of the second sample, and so on. And then note that the first feature is always 1, so this corresponds to the bias unit. And this is the square, the fourth feature is the square of the first feature in the original feature matrix. The The next feature, or the fifth feature, is the feature based on the interaction between these two terms, which is the product of these two features, original features, which is the fifth feature, and the sixth feature is the square of the second feature from the original feature matrix. So this particular quantity over here is square of this particular quantity. The next step is to split the training set into training and test set. So here we take the polynomial transformed feature matrix and the label vector and split it into training and test sets. We again make sure that the number of rows in the training feature matrix and training label vector are the same, and the same check is also extended to the test set. Next, we plot the training data in original feature space and check its distribution. So you can see that there are examples from two classes and they are arranged in a circular manner. So class 1 and class 2 are separated by some kind of a circular decision boundary. As a next step, we train a logistic regression model on the training set and visualize the model and the learning curve. So here we instantiate logistic regression object and use the gradient descent procedure with regularization rate of 0. That means we are not using any regularization penalty for training the model. We train the model for 10,000 epochs with learning rate of 10 raised to minus 2. And what we have printed here is the final weight vector. And you can see that there are 6 different values in the weight vector that is printed out here, corresponding to 6 features that we learned from the polynomial transformation. So here we have plotted the learning curve with the iteration number on the x-axis and loss on the y-axis. So after 10,000 iteration or 10,000 epochs, we have reached almost a zero training error. And we can visualize the decision boundary learned by the logistic regression classifier. And because we use the polynomial transformation of degree 2, we are able to learn the circular decision boundary between two classes. And as a next step, we evaluate the model performance on the test set, and remember that test set was set aside for evaluating the model performance. So we obtain the labels for each test sample using the predict function of the logistic regression class. Then we calculate several classification metrics through classification report utility from sklearn.metrics. Here we have kind of obtained a perfect classifier with precision recall and F1 score as well as accuracy as 1. Now remember that this is a toy setting and such a perfect classifier might be very hard to obtain on a real world dataset. So in this video, we used logistic regression model to learn a circular decision boundary between two classes. This was an attempt to introduce you to the world of using polynomial transformation in the logistic regression setting. So there will be many such kind of cases in real world where we need to use polynomial transformation, and this demonstration helps you to get a feel or get you an idea about how to use polynomial transformation in the logistic regression setting. In the next video, we'll try to visualize the loss function and the gradient descent trajectory for this toy two-dimensional feature matrix case.